Greetings. Welcome to my video series on AP Physics C, Electricity and Magnetism, where I'm going to be covering an introduction to electric fields in this video. Now, electric fields are a topic in physics that tend to make first-time learners a little uneasy. I know that it certainly did for me when I was first learning them. So one of my goals within the conceptual slides today is to help you come to terms with them as an abstract idea that works as a means to an end conveniently if it helps us work better with electrostatics. Afterwards, I'm going to do a couple of examples that show how they can be used, including a way that can predict the motion of moving charges. So, without further ado, let's get started. Now, with all of the abstract weirdness that's about to ensue, I figured I'd give some historical background to show that really you're not alone. So, in introductory physics, electrostatics, just being one example of this, there are a handful of forces that seem like they're interacting with other objects at a distance with no actual direct contact. Now, this contradicts our intuitive understanding of how forces work. Anytime a force is applied, there's usually a medium through which it's conducted, such as a hand, air particles, surfaces, ropes, etc. But when Isaac Newton was formulating his theory of universal gravitation, he threw out that intuition and created a mathematical model that almost perfectly linked the motion of the stars to the physics that we know and love on Earth's surface. But even though the model worked, it didn't mean that Newton was happy with a lack of understanding of why it worked. So this action at a distance, as it was called, made him notably uneasy. Quoting him, he stated, "Action at a distance is so great an absurdity that I believe no man who has a competent faculty of thinking could ever fall into it." Basically, he's saying that his model is just a model, and that only an insane person would think that forces could actually be conducted wirelessly like that. I mean, come on. But seriously, the question remains, what medium allows force to be exerted over large distances like that? Is gravity even a force at all? Is there some invisible gravity particle that drives the interaction? Physicists back then had absolutely no idea. And because of that, they moved on to more pressing solvable matters. Now, we understand the mechanics behind the action at a distance a little better today. And though they are beyond the scope of this video, I would like to encourage you to go down that rabbit hole yourself, if you so choose. Whatever the case, action at a distance, for the moment, was an acceptable concession to make for these physicists. And it was shown and demonstrated by gravitational force, electric force, and magnetic force. So to better help characterize action at a distance, it was assumed that objects that exerted these forces created invisible fields around them that are capable of exerting forces on each other. And that assumption is the tool that we are going to be investigating in this video. So a big idea to understand upfront is that fields exert forces on objects similar to the source of that field. For that reason, fields are directly influenced by how much of a certain quantity is within that field. Field strength can be roughly described by how much force due to the field is experienced by the quantity that's affected by that field. So we're going to see here that charge is a producer of a field. So how much charge is placed within an electric field directly influences how much force that charge feels. Now, there are two major quantities that we've studied so far that produce these. Like I said, charge, but also mass. And since we're likely a little bit more comfortable with gravity, I'm going to show you that one first. Now, mass is a quantity that produces gravitational fields. And because the field is produced by mass, it by definition exerts force on other masses. The gravitational field is actually a familiar quantity, and you probably didn't realize that this was describing a field the whole time. But going by our rough equation for the field strength above, a gravitational field, G, is given by the gravitational force divided by mass. This is effectively our classic formula for gravitational acceleration, lil g, which has been a gravitational field this whole time. How about that? Now, if we substitute in the equation for universal gravitational force, we have a more general formula for gravitational field that incorporates the distance from the source mass. Now, lil g has two unit representations. It is an acceleration, as we already know, so it can be described in meters per second squared. But a more traditional way to represent field units is units of force divided by units of mass, or units of producer in this case. So in this case, it would be newtons per kilogram. This representation helps to describe that a field is telling us how many newtons of force will be exerted at a location for every kilogram of mass that we place there. Finally, the direction of the gravitational field, no surprise, will always point toward the mass producing that field. Gravity is a naturally attractive force, and the field lines tell us that everything must go inwards. Now, let's see how similar things are with electric fields. Charge produces electric fields, and so electric fields will exert forces on other charges. And as we can say, an electric field is an electric force divided by the affected charge, That is already one equation that we can use for electric field. However, we can also substitute in Coulomb's law for the electric force and reach a general formula for electric field that looks like this. Really, it is just Coulomb's law, but without a charge at the location that you're analyzing, so it's without the little q. Units for electric field are best and most commonly described by newtons per coulomb, meaning that an electric field tells you exactly how many newtons of force will be exerted at a location for every coulomb of charge that you place there. And finally, electric field does differ quite a bit from gravity in how the direction works. I've got a little picture here that you can use as a reference. Electric field vectors will point toward negative source charges, and they'll point away from positive source charges. So just think that positive charges are radiant little fellows, like this guy here, and negative charges are self-centered. Everything's going to go in towards them. And while I work on better mnemonics for that sort of thing, you should really internalize this rule right here. It's really crucial that you understand it, just because it's going to help correctly set up direction for pretty much everything else you're going to be doing in this unit, as well as many others going forward. So make sure you know it, and let's delve a little deeper. Now, more on electric fields specifically. Mathematically, electric fields are called vector fields, and you can think of them intuitively as maps that predict what will happen if a test charge is placed at a certain location. Now, the test charge I mentioned there is something I'll be bringing up and using a lot. I like to denote it with lowercase q, and you can think of it as a hypothetical or literal charge placed in an electric field that will experience a certain force in a certain direction. It's worth noting that electric fields are abstractions. On their own, they truly cannot be seen without observing their physical effects. So in order to make more intuitive sense of them, test charges are tools that we use to predict those physical effects. And in that way, we can make electric fields a little bit less abstract on paper. To demonstrate this, say we have a negative charge in space somewhere. This negative charge will produce an inward-facing electric field because it's self-centered. At some location in space around this charge, we'll call point P, we'll say that the electric field strength at point P is 5 newtons per coulomb. Again, as it stands right now, this field will not do anything and will not be seen until we give it something to do. So, for that reason, we'll place a positive test charge, plus Q, at point P. And if we do that, well, our formula for electric field tells us that a force will be exerted for every coulomb of charge that we place at point P, given by this equation here. Rearranging that and plugging in, we can now say that our positive test charge will experience 5 newtons of force for every coulomb that it has. So if our test charge has 1 coulomb of charge, it will experience 5 newtons of force. If our charge has, let's say, 2 coulombs of charge, crazy, I know, it'll experience 10 newtons of force. Note that the logic behind this is effectively just Coulomb's law with a fresh coat of paint. You might wonder why we go through all of this trouble when we already have a formula that works perfectly fine. My answer is that physics sometimes is at its best when we're able to make a more convenient formula for something. We were able to do things much more easily with gravity, for instance, when we didn't have to plug in Newton's law of universal gravitation for every single dynamics problem that you did. That would have been horrendous. And even though, Newton's law of gravitation is the more correct formula, it's just not practical in that moment. So electric fields allow us to do some of the same. We're leaving out certain factors like that extra charge that doesn't need to be there until we actually need it. And in that way, we can make potentially complex problems a little bit easier. So if you can live with that, electric fields are largely what we're going to be using from here on out. Lastly, I need to clarify some important details with direction. Now, electric field is a vector quantity, so direction does matter. And the good news is, it does behave exactly like any other vector in how it's added, subtracted, or multiplied. For instance, say that there's some point P directly between a positive and a negative charge, like we've got over here. Now, at point P, the electric field due to the positive charge will point away from its source. And let's say the magnitude of that field is 5 newtons per coulomb. The field from the negative charge will point inwards towards its source, and also with a magnitude of 5 newtons per coulomb. In a setup like this, the field vectors will combine together to a total of 10 newtons per coulomb to the right at point P. Now, if we alter that scenario a little bit, so instead we have a positive charge at both locations on either side, then there's going to be an electric field vector pointing to the left and to the right with equal magnitude at point P. In this scenario, the electric field vectors will cancel out with each other. So the total electric field at point P will equal 0 newtons per coulomb. A charge placed at this location would experience 0 newtons of force regardless of how much charge it has. Now that's simple enough, but there's one more component to all of this, and that's that the effects of the electric field on a placed test charge within it involves what sign that test charge is going to have. This goes back to our rules of attraction and repulsion. A positive charge attracted to a negative charge, and a negative charge will be repelled by another negative charge. For electric fields, we can apply this rule by thinking about the direction of force relative to the direction of the electric field vector. So going back to our example from the previous section, note that the direction of the electric field lines are running along point P. If we place a positive test charge at point P, it'll experience a force in the same direction as the electric field. You can think of this in terms of what the positive charge wants to do. If it wants to move towards the negative source charge, and so it experiences a force in that direction. But if we instead place a negative test charge at point P, it'll experience a force opposite the direction of the electric field vector. Again, think about what the test charge wants to do. If it's negative, it'll want to get away from the negative source charge as soon as possible. And so it experiences a repulsive force. But in general, it is most important to remember that field lines don't always point inwards or outwards towards the source charge. So remembering these rules is especially important for those cases, kind of like on this picture from before. Now, keeping those concepts in mind, I'm going to now delve into 3 different examples of how to work with electric fields. So let's go. Testing. All right, for this first example, we have a person of mass m standing in a special chamber built to create an electric field. Interesting. The floor has a net negative charge and the ceiling has an equal net positive charge, giving the inside of the chamber some electric field E. Lastly, we're going to say that this person carries some unknown charge Q. We don't know what it is, but we'll figure it out. So the first thing we need to figure out before anything else is exactly what direction the field has in this chamber. Now, this chamber has what we're going to call a uniform electric field, which just means that it's pretty much the same throughout. I won't go into specifics as to why it stays uniform throughout yet, but we will cover it later on in a different unit. Now, there are a couple ways that you could justify this. One is that generally an electric field is going to tend to run from positive to negative. So just based on that alone, we can say that this electric field is likely to be going from top to bottom or from ceiling to floor. Now, another way that you could justify it is to think about what a positive test charge would want to do. Say we place a positive test charge somewhere in this field, right here, and it's positive. Well, this positive charge is going to want to get away from the ceiling as soon as possible, and it's going to be very attracted to the floor. So you've got the ceiling exerting a force pushing it downwards, and then you've got the floor exerting a force pulling it downwards. And so overall, this charge is going to really want to go downwards. And as a result, we can safely say that this electric field is going to be pointing downwards. Now, overall, I would say the main reason you'd want to give yourself for justifying something like that in the future is largely just that electric fields tend to point from positive to negative in general. Okay. So next, we need to figure out the sign of the charge on the person if the person is lifted up by the electric force. So we're straight up levitating this man. Now, to think about this, you want to go back to your rules of what force or what the direction of force takes from the direction of the electric field. If the person is lifted up, that odds are means that the electric force is opposing the force due to gravity, which we'll assume that we have here. So say that this person has a gravitational force exerting on them downwards. We want our electric force to be pointing upwards. Now, if we want our electric force to be facing upwards, we should think about what charge this person would need if that's going to oppose the downward direction of our electric field vectors that he's passing through. And well, if the force has the opposite direction of the electric field vector, that by default should mean that the charge on this person is negative, largely because negative charges experience force opposite the direction of the electric field vector. Don't forget it. All right, and finally, we have the meat and potatoes of this problem, finally. So this person, if we assume that they have a mass of 100 kilograms and the electric field strength is 3 × 10⁶ newtons per coulomb, that's 3 million newtons for every coulomb. What charge must the person have in order to be lifted up? So here, we've got a couple of things that we need to consider. First is just the basic mechanics behind this. We're looking really for the minimum charge that they need in order to be lifted up. And because we're looking for a minimum charge, we can also think about it in terms of the minimum force that's needed in order to lift them up. Now, if they're to be lifted up, they could have any force larger than this minimum force, but the absolute minimum that's needed is going to be when the gravitational force pulling them down towards the floor is at least equal to the electric force pushing them upwards. That way, the person could at the very least be at equilibrium, so they could jump upwards and then they would just float at constant velocity up to the ceiling until something stops them. Now, that's the case, well, we should kind of elaborate a bit more on our equations that we're setting equal to each other here. Force due to gravity is pretty much the standard usual one. It's going to be mass times acceleration due to gravity. Although really now, in terms of our definition of gravitational field, it's really that the gravitational field, little g, is equal to the force of gravity divided by the mass. Interesting. Now, the next thing here is our definition of electric field. We would generally say that that's the electric force divided by some amount of charge that's within that field. But if we rearrange this to solve for the electric force, then we could say electric force is generally equal to Q times E, where little q is the charge inside of the electric field. Now you note here, I did actually add a little tail to my q's. That's mostly a handwriting thing to distinguish my q's from my 9s, because if you know from Coulomb's law, 9 does pop up a lot in this unit, so it's to avoid some confusion there. You might need, I might recommend adjusting your handwriting a little bit with electrostatics, because there are a lot of letters that tend to pop up in different places at different sizes, and if you can distinguish them between each other a little bit, it goes a long way in just avoiding misinterpreting your work, especially if your handwriting isn't so great at the moment. Whatever the case, we now have our equation to set up and substitute some stuff into. So over here, we're going to say that mg, force of gravity, is equal to QE, which is electric force. Now to solve for Q, all we really need to do is rearrange. So Q, the charge, is going to equal mass times acceleration due to gravity divided by big E, which is our electric field strength. And with that, we can plug some stuff in. The mass is 100 kilograms. Lil g is always 9.8 meters per second squared, at least on Earth's surface. And then our electric field strength is 3 times 10 to the 6. So again, I'm going to use my little shorthand here, 3 times 10 to the 6 newtons per coulomb. Note that I did also change my shorthand a little bit from the last video. This is mostly just so we didn't end up confusing, lowercase e with elementary charge or exponential e or anything. Big E is how it appears in a calculator, so it's just a little bit closer to the actual calculator shorthand. Okay, and so if we plug all those numbers into a calculator and we evaluate, we should find that the charge on this person needs to be at least negative 0.33 millicoulombs. Milli, again, meaning 1 times 10 to the negative 3, kind of like millimeters. And it's very important that you do denote that this should be a negative charge, not a positive charge, because if you made this a positive charge, then you're basically just going to crush this person, because then the electric force would be pushing downwards in addition to the gravity, and we don't want that, okay? So with that, that's pretty much our main tabletop example out of the way. The next one's going to be a little bit more abstract, so let's jump over to it. All right, our goal now is to determine the total electric field with magnitude and direction at point A, right here in the middle, based on the diagram shown below. So here, this is looking pretty familiar. We have 3-point charges. This problem's going to be a lot less tedious though, because we're not going to have to find the electric field at like the position of each of the 3 charges. So here, the first thing we're going to do right off the bat is color code these charges. So I'll make this guy over here blue, no particular reason why. I'll make this guy over here red, and I'll make this guy over here green. That's just to help organize our forces a little bit better. Now, the next thing that you might note is that none of these 3 have labels. Now, I would recommend that you actually go through the effort of labeling them. So I'll name this guy Q1, this one Q2, and this thing over here Q3. Now, it may seem like it's extra work, but I highly recommend you do this mostly, again, to keep yourself organized, because it's going to be very easy to lose track of these things sometimes, and just giving each of these things a label and a name helps a lot when you're like trying to call onto them later in different problems. Finally, before we actually do any math, I think it's good just to go ahead and sort out the directions up front. So we're going to use our kind of principles that we used in the slides earlier and say that, well, Q1 here is a negative charge. So all electric field forces, or all electric field vectors are going to be pointing towards itself. So since Q1 is on the left side of point A over here, that means that the electric field due to Q1 is going to be pointing to the left towards Q1. We will call that E1. Next, with Q2, it's a positive charge, so all electric field vectors are going to be pointing away from that charge. So at point A, that means that E2 is going to be pointing to the right over here, away from Q2. And then finally, Q3 is also a positive charge, so it's going to be pointing away from Q3. And since it's on the right side of point A, note that here, the forces, or the electric field vector, is technically pointing to the left relative to point A, okay? And we will call that E3. So we have two electric fields pointing to the left, and then one pointing to the right, and those are going to add together or subtract together as vectors, okay? Now with that in mind, the last thing is that our equation that we should be using for electric field here is really just going to be the Coulomb's law variant. So it'll be Coulomb's constant times the absolute value of the charge that's producing the field divided by the distance between point A and whatever charge we're looking at. Now again, I do absolute value around the charge there, just to again avoid any confusion that might pop up with positives and negatives here, because we're going to try and keep the directions separate from the math that we're doing, just so you don't accidentally mess that up. Okay, so down here we're going to find E1 first. Now electric field due to charge 1 is going to be Coulomb's constant, which is 9 times 10 to the 9, times the charge from Q1, which is 1 times 10 to the negative 3 coulombs. It's 1 millicoulomb. And then we're going to divide that by the distance between Q1 and point A. So that'll be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 meters based on this little scale factor over here to the right. So it'll be 10 meters squared. Plugging those numbers into a calculator and solving, we should find that E1 is a whopping 90,000 newtons per coulomb to the left, based on our arrows above. That's a very large number. You're going to find that electric field values tend to be pretty large, and that's okay, because usually what's going to happen is you're going to put a very small amount of charge into that field, and so the final force as a result is going to be pretty close to what you'd expect. Okay, with that in mind, let's get E2 over here. So E2 is going to be pretty much the same equation, just a different charge. So it'll be, again, Coulomb's constant, 9 times 10 to the 9, times 36 microcoulombs. Note that the scale factor changed a little bit. Micro, mu, is 1 times 10 to the negative 6. So this is going to be 36 times 10 to the negative 6 coulombs, all divided by the distance between it and point A, which is 1, 2, 3 meters squared. Plugging those numbers into a calculator, we're going to find that E2 is 36,000 newtons per coulomb, and it is pointing to the right. Don't forget that direction. Finally, let's do E3. So E3 over here is due to charge 3, and again, it's going to be Coulomb's constant, 9 times 10 to the 9, times the charge of Q3, which is 100 microcoulombs, so 100 times 10 to the negative 6, divided by the distance between it and point A. So that'll be 1, 2, 3, 4, 5 meters squared. Plugging those numbers in, you're going to find that it pretty much matches E2 in magnitude. It's going to be 36,000 newtons per coulomb. However, as noted from our direction stuff above, this one is going to be acting to the left. So it will actually cancel out with E2's electric field strength. Interesting. Okay, so now that we have all of those, really the final goal here is to find the net electric fields. That'll be E net. And really it's just adding these three vectors up. None of them are in different directions. They're all parallel to each other. So we can just do E1 plus E2 plus E3 without any issues. Now note here that E2 and E3, because they're equal and opposite, are really gonna just knock each other out. So these will both add to 0. That leaves us with just E1 as our net electric field. So here, our net electric field is gonna be 90,000 newtons per coulomb, acting to the left. And that is our electric field, okay? So finally, we actually are gonna do something with this field. So it's worth clarifying that up until this point, all of this stuff is abstract. You would never be able to actually see any of this stuff if it was just these charges alone. The closest you would really be able to get is that these charges are going to affect each other. And so like the electric, this charge Q2 is in the electric field produced by these other two charges here, and it will move thusly. But how we're going to see the electric field at point A, assuming all of these charges are held in place, is by placing a test charge here. And that's what this thing is right here. So if we place a negative test charge, so this is Q equals negative 1 times 10 to the negative 3 coulombs. If we place that charge at point A, we're going to now find the force based on its magnitude and direction that would be acting on that charge. So this is the visible effect that we'll actually get out of this electric field at that point. So here, it's worth noting that this is a negative charge. And so it's important not to forget that negative charges are going to experience a force that is opposite in direction from that of the electric field vector at that point. So our electric field vector points to the left. That means that the force that this charge experiences is going to be acting to the right. Okay? With that in mind, the math here is actually not that bad. Using that equation that we got from the last problem, we can simply say that the force the electric force experienced by this charge is going to equal the absolute value of the magnitude of this charge times the electric field strength. And again, I'm doing absolute value here, just so again, we don't worry about positives and negatives messing up our sense of direction here. We will do that separately. And so here, It's going to be the magnitude of this charge, which is 1 times 10 to the negative 3 coulombs, times our electric field strength, which is 90,000 newtons per coulomb. And so the force experienced by this charge, if you do all the math, is going to equal 90 newtons. And again, it's going to be electric fields to the left, so this force is going to be to the right. It'll be 90 newtons to the right on this charge. Okay, and that is our problem done. Okay, so again, very important that you're extra careful with direction here. There's a lot of sources of confusion, and every year that I teach this stuff, I see mistakes happen with direction primarily. So just be careful with that. Okay, this next one here is going to be quite an interesting example. This is going to be our first non-electrostatics problem. This is going to be a problem in which we have a moving charge, and we're going to find the motion of it. So let's try it out. Now, before we get going with this one, I want to establish a big idea up front, which is that if a charge is traveling through a uniform electric field, it's going to experience a constant force and acceleration. Now, this topic, or that idea, shouldn't seem too crazy to you, because we've dealt with it many times before. In mechanics, if we are establishing little g, or Earth's acceleration due to gravity, as Earth's gravitational field, at least at Earth's surface, well, we've been dealing with things moving with a constant force and acceleration through that field for pretty much half a year. When an object is thrown through the air, it is experiencing a constant force and acceleration due to Earth's uniform gravitational field. And so we are just simply applying that same logic to a charge moving through this uniform field in this problem. So with that, we have a charge, which is given an initial kick. It takes 3 times 10 to the negative 16 joules of energy to accelerate a proton up to this crazy speed, which is 600 kilometers per second. So suppose that this proton is projected horizontally into a uniform electric field that exists between these two plates here, as given by this little shaded region. The proton is going to move 6 meters horizontally before it strikes one of the plates on either side. And we're told that we can ignore gravity here. Okay, so this problem is very interesting. It's kind of a particle accelerator adjacent problem. We're showing how much it's going to take to deflect this particle upwards to hit one of the two plates. This is a pretty common experimental setup when you're messing around with charges and trying to conduct where they go. So the first thing here is I want to break down this problem into something a bit more familiar to most of you. And first, we're going to start with looking at what the trajectory is doing. This proton, once it launches into the field, is going to travel through what looks like a quadratic trajectory. Okay, so think about what types of problems you've seen something like that happen before. In fact, if you were to take this problem and flip it upside down, see if it looks a little familiar to you. The next thing I'm going to note is this whole thing about the uniform electric field. This particle is traveling through one, and so we can assume that that uniform field is accelerating the object constantly. Okay. So with that in mind, again, think about where you've seen that before, especially in combination with this quadratic trajectory. And you might have already caught on, but this problem, especially if you flip it upside down, is really no different from a horizontally launched projectile. And so really, this problem is just an example of projectile motion. It's just that here, by definition, it's not necessarily projectile motion, just because a projectile relies on Earth's uniform gravitational field. Here, we're going to be treating this proton as a projectile through this little apparatus's uniform electric field. So with all that in mind, I'd say that you can generally use the same points of logic that you normally use for kinematics or projectile motion to solve this problem as well. So let's take a look at what we need to do. So this problem is going to be broken up into 3 different parts. The first task is to calculate how much time elapses between the proton entering the field right here and it's striking the plate over here. So to do this, well, let's take a look at what information we have already. We know that this projectile is going to be launching with a horizontal speed of 600 kilometers per second. So we'll note over here that our initial velocity in the x direction is 600 times 10 to the 3 meters per second. That's kilometers, kilo. Okay. We also know that the horizontal distance is going to be traveling. So we can relate that to our horizontal velocity. So we know that our delta x right here is going to be 6 meters. No conversions we need to do there. And so if we're treating this like a projectile motion problem, we want to find the total time elapsed. Well, we have a pretty nice equation that involves the horizontal direction, where we're going to assume that this proton isn't accelerating. So if we take a look at this kinematic equation, that delta x, the displacement in the horizontal direction, is equal to the velocity in the x direction times the time that it's traveling. Well, we basically have everything we need to solve for the total time. So rearranging a little bit, all we need to do is take the displacement, delta x, and divide it by the speed it's traveling with, which is v naught x. So let's go ahead and do that over here. Our time, or our total time elapsed, is going to be our displacement of 6 meters divided by 600 times 10 to the 3 meters per second. And by running the numbers on that, we should find that this proton will smash into the wall of this apparatus in about 10 times 10 to the negative 6 seconds. Or if you want to condense that down a little bit, you could also say that that is going to be about 10 microseconds. It's a very short amount of time. Okay, so with that, our next task is to determine the acceleration of the proton while it is in the electric field. Now for this, we're looking for an acceleration. So let's go ahead and note our goal right there. Now note that the proton is accelerating in the y direction, the up and down direction. So we should really look for information that we have in that direction. Now first, we know the displacement that the proton has in the y direction. It's 0.6 meters, as given by the dimensions of the apparatus up here. So we'll note that our delta y is 0.6 meters. And then we also know the initial velocity in the y direction. It's going to be 0, because it's a horizontally launched projectile. Remember that if it explicitly tells you that it's launched horizontally, that is an assumption that you can make for information. Now we need one more piece of information in order to make any of the kinematic equations solvable. And we have one right up here. Time is a really nice quantity in projectile motion because it connects to both dimensions. It connects to the horizontal direction just as much as it connects to the y. So by noting that this thing is going to be in flight before about 10 microseconds, 10 times 10 to the negative 6 seconds, well, we have exactly all the information we need to figure out how long it was accelerating for. So over here, we need to find the right equation that connects all of this information together. And the equation for the job here is going to be change in y is equal to v naught y times total time of flight plus 1/2 acceleration times big T squared. This is our classic projectile motion problem. So here, it's worth noting that we can pretty much knock out this term entirely because v naught y is 0. And so when plugging things in, we're left with 0.6 meters equals 1/2 times our acceleration times our total time squared, which is going to be 10 times 10 to the negative 6 seconds squared. So at this point, we just need to rearrange to solve for acceleration. So our acceleration, if we rearrange, is going to equal 2 times 0.6 divided by 10 times 10 to the negative 6 squared. And crunching the numbers on that, this proton will have an unfathomably large acceleration of 120,000 meters per second squared. We're a long way from 9.8. Now, even though this acceleration is unfathomably large, keep in mind that this is a very small and very light object. This thing has a mass of 5/3 times 10 to the negative 27 kilograms. So even though this is a really large acceleration, keep in mind that, it's a very small object. So it takes very little force to accelerate something as light as this to those sorts of speeds, or to those sorts of, accelerations. Okay, and that brings us to our last task here, which is to find the strength of the electric field between the plates. So here, since it's asking about electric field, I'd say it's a good thing just to go ahead and state an equation for electric field. Here, we already have the charge and everything, so I think the force, or the electric force experienced by the charge, we'll just say force experienced by the charge divided by the charge in the field itself is equal to electric field. Now here, we actually are pretty much exactly in the state that we want it to be. We just need to expand out something here. Well, we know the mass of the proton based on this information right here, and we know the acceleration of the proton, and so there's no reason we can't use good old Newton's second law here, that force is equal to a mass times an acceleration. Then we know the mass of the proton, it's 1.6 times 10 to the negative 19 coulombs, so we can still divide it by that number. And in doing so, we basically have our equation that we need to calculate electric field. So plugging things in over here, we can say that the mass is 5/3 times 10 to the negative 27 kilograms, very light. The acceleration we know is 120,000 meters per second squared, and we're dividing all of that by the elementary charge, which is 1.6 times 10 to the negative 19 coulombs. Okay, so taking all of that and multiplying it all together, we'll find that the electric field experienced by this guy is 0.00125 newtons per coulomb. That is a very, very, very small electric field value compared to what we'd had in the last two examples. Now again, note that even though this is a very small electric field, that's still going to do a lot to this proton, as seen by the acceleration here. So electrostatics is going to have a lot of weird intuition that you'll need to employ if you want to make sense of the scales of these things. This is an extremely unfathomably small object. Remember, this is subatomic. And so it doesn't take much to get this thing to do pretty extraordinary things. And if you can kind of let your brain accept some of that stuff, electrostatics is quite interesting in how we're able to control the motion of these unfathomably small things. So with that example, that's pretty much all I have for you. Thank you very much for watching. I hope not only the examples helped give you an understanding of how to apply electric fields, but I also hope that I was maybe able to make you a bit more comfortable with the idea of an electric field as well. In the next video, I'm going to cover some slightly more complex examples that involve electric fields in 2 dimensions, as well as how to start employing some calculus into all of this stuff. So until then, thank you very much for watching. Peace.